Now we know that water forms hydronium and hydroxide ions in water. When something acidic is added into water, in order to be acidic in the first place, it must somehow increase the concentration of hydronium ions in water. And already we know that the concentration of hydronium ions in water is directly related to the concentration of hydroxide ions in water through Kw. So to make a solution more acidic, we must shift the equilibrium in favor of more hydronium ions. This can be done in several ways. Recall your Le Chatelier's principle. You can increase the concentration of hydronium indirectly by adding something that reacts with water to give you hydronium. For example, ethanoic acid, which reacts or dissociates in water to give you ethanoate and hydronium. Now that the concentration of hydronium is increased, the reaction quotient of water's dissociation, Qw, will be larger than Kw. This will cause a backwards reaction, moving towards the formation of water, which in the process requires using up hydroxide ions. So hydronium ions and hydroxide ions are both consumed until the product gives you 10 to the power of negative 14. In any case, if the concentration of hydroxide at equilibrium is reduced, then it only makes sense if the concentration of hydronium at equilibrium is increased. This is multiplication, so if one side reduces, the other side must increase to give you the same result. So in short, that means that the pH of the solution decreases compared to before adding any acid, and the acidity of the solution increases, intuitively of course. So you get how exactly this dissociation of acids in water actually decreases, sorry. But let's go back to the dissociation reaction again. Ethanoic acid is a weak acid, meaning that it does not dissociate fully. This too is a reversible reaction. How much does the acid dissociate? So here is where we bring up the equilibrium expression, which is ethanoate multiplied by hydronium over ethanoic acid. This is a special K because it represents the dissociation constant of an acid, and we call it Ka. It is important to note here that the concentration of hydronium is not the same as the concentration of ethanoate, as you would have concluded at the end of the previous lesson when we were solving equilibrium calculation questions using the ICE table. This is because hydronium is already present in water and it is also subject to the equilibrium that it has with water and hydroxide ions. We will look further into this relationship in the next checkpoint. If we looked at the Ka of an acid, how can we tell if it's a relatively stronger acid or base? Recall the equilibrium expression of Ka. If Ka is larger, it is simply the case that it produces more products, meaning it dissociates to a greater extent, producing more hydronium ions. We can also apply P to Ka to create the term pKa. The higher the Ka value, the smaller the pKa value, and the more acidic the solution becomes. In the same way, for weak bases such as methyl amine, it reacts with water to produce the methyl ammonium ion and hydroxide ions, which again is a reversible reaction, represented by the following equilibrium expression, which you should already be able to come up with. And again, the hydroxide concentration is not the same as the concentration of methyl ammonium because hydroxide is already present in the water. This equilibrium expression is once again a special equilibrium expression, and we call it Kb. Surprise! If the Kb value is high, the pKb value is low, and the solution is more basic. Now let us move on to understanding more about the relationship between Ka, Kb, and Kw.